Water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w of t is measured in degrees Fahrenheit and t is measured in minutes. At time t equals 0, the temperature of the water is 55 degrees Fahrenheit. The water is heated for 30 minutes, beginning at time t equals 0. Values of w of t at selected times t for the first 20 minutes are given in the table above. So part A, use the data in the table to estimate w prime of 12. Show the computations that led to your answer using correct units. Interpret the meaning of your answer in the context of this problem. Okay, so w prime of 12. That is going to be our first derivative. So the problem here, though, is that we don't have the actual function itself. So we can't just directly take a derivative. We're going to have to do an estimate. Now, it's looking for w of 12. So we know, looking at our table up here, that we're going to be somewhere between these 2 points. And we do know that our graph is strictly increasing, and I just put a little graph in there to kind of make it easier to visualize. So we know that our point 1 time is 12 is going to be somewhere maybe in here. I'm not sure exactly where, but somewhere in there. And what we should recognize is that the point at t equals 12 is actually exactly halfway between 9 and 15. They're both 3 minutes away from 12. So in this way is 3, in this way is 3. So we can actually use a secant line to sort of estimate our tangent line. So our secant line is going to look something like this. And we know it's going to go probably somewhere around where our midpoint is here, where our t equals 12 point is. So we're going to just use our knowledge of slope and find the slope of this line, and that'll give us a decent approximation of w of 12. So remember, slope is just rise over run. So our rise is going to be w of 15 minus w of 9. That's essentially our y2 minus y1. And that's going to be divided by our x values here. So 15 minus 9. All right. Then we know w of 15 is actually, we're given that information in the table, 67.9. And w of 9 is going to be 61.8. When we do that out, we end up with 6 1/10 divided by 6, which is going to get us approximately 1. I think it's just a little over 1. I'll go ahead and do that calculation. 6.1 divided by 6. We're going to end up at about 1.017. And we also need to know, using correct units, Interpret the meaning of your answer in the context of this problem. So what we just found was the rate of change with respect to time, rate of change of temperature, that's our f of x value, with respect to time in minutes, which is our x value. So it's going to be 1.017 degrees degrees Fahrenheit. It's going to be an increase, so it's positive. And this is per minute, specifically at the 12-minute mark. So again, all we did was we used this secant line to kind of approximate what our tangent line might be at this point right here, right at 12. All right. Use the data in the table to evaluate the definite integral from 0 to 20 of w prime t dt. Using correct units, interpret the meaning of the integral in the context of this problem. So again, we don't have any specific function defined, but in this case we don't actually need that if we can remember what the relationship between integrals and derivatives is. So in this case we have the definite integral of a derivative, of the first derivative. So that definite integral of the first derivative is just going to get us our original function, which in this case is given up here in our table. So the definite integral of 0 to 20 of our first derivative of our function is actually just going to be our original function evaluated at 20 minus our original function evaluated at 0. So that's going to be, and we do have our data up here. So the integral, the function evaluated at 20 is going to be 71. And integral evaluated at 0, 55, which gives us 16. But we also need to interpret the meaning in context. So thinking about units, the original function, it gives us our units right here. It's in degrees Fahrenheit. And we know we are essentially taking our ending value and subtracting our starting value. So all this really means is that our integral here, our definite integral, represents a 16 degree Fahrenheit increase in temperature over the course of 20 minutes. And that's it. Okay, part C. For 0 is less than or equal to T, which is less than or equal to 20. The average temperature of the water in the tub is 1 over 20 times the integral from 0 to 20 of W of T dt. Use a left Riemann sum with the 4 subintervals indicated by the data in the table to approximate. Does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. So this is just kind of a variation of the average value theorem or the mean value theorem. And it just requires us to approximate first using some Riemann sums. So this is the left. This is left Riemann sums. So I have our graph from the last problem, and I'm going to just kind of show what left Riemann sums would look like here. So we're going to use our leftmost point, make a rectangle. There's our first one, and we're going to have 4 subintervals. Okay. Using our leftmost point again. Okay, so that's what that's going to look like. And we just have 4 rectangles. So let's go ahead and calculate the approximation of our integral, and then we'll go ahead and multiply it by 1 over 20 to get our solution. All right, so the first rectangle is, let's see, it's got a length of 4 and a height of 55. So we're going to do 4 times 55. We're going to add. You can look at our next one. Interval is length 5 times 57.1 plus our next interval length is 6 times, let's see, 61.8. And then our last one, we're going to do 5 times 67.9. And when we calculate that, we're going to get 1,215.8. And if we do 1 over 20 times, again, this is the approximation of our integral right here. If I do that out, 1 over 20 times 1,215.8, I'm going to get 60.79 degrees Fahrenheit. Okay, does this approximation overestimate or underestimate the average temperature of the water over these 20 minutes? Explain your reasoning. So the thing to keep in mind about this one is that it's strictly increasing. So it's always going up. And you can probably see from my graph right here that this is definitely a underestimation, because I have all this empty space in here. Yeah, so that's going to be an underestimation. And if it's strictly increasing and you use left Riemann sums, it's always going to be an underestimation. If it's increasing and we had used right Riemann sums, it'd be an overestimation. So I guess if I were answering this on a test and it said to explain my reasoning, I would just say because the function is strictly increasing and we're using left Riemann sums, it's always going to be an underestimation. Okay, for 20 is less than or equal to t, which is less than or equal to 25. The function w that models the water temperature has first derivative given by w prime of t equals 0.4 square root of t cosine 0.06 t. Based on the model, what is the temperature of the water at time t equals 25? So this problem, I'm working under the assumption that calculators are allowed. If not, I can do this problem a little bit differently, but I'm going to work under that assumption for now. Okay, so we are going from 20 to 25, and just looking at our original table, it kind of stops at 20, right? Or at time t equals 20. So what I would do is see kind of figure out what we know about this. So we have the first derivative here, w prime of t, and we know that the integral of that would give me the temperature change from 20 minutes to 25 minutes. So I'm actually gonna start by finding out what that value is, because that's pretty important. So integral of, or from 20 to 25. Apologies, I'm writing with my mouse. It's not the fastest. 0.4 square root of t cosine of 0.06 t dt. Okay, and when we calculate that, again, I'm assuming that we are able to use a calculator here, gonna get 2.0431 5. Now, one thing that we have to keep in mind is this right here is actually, right, w prime of t, which means when we take that definite integral of our first derivative, we're essentially ending up with our original function from 20 to 25. And I'll kind of write that out a little bit more explicitly. So we're saying that this value right here that we just found, that's our temperature change from 20 to 25. So I'm going to go ahead and put that right down here. And we know that that is equal to our temperature change from 25 to 20. So essentially this, W of 25 minus W of 20. Right, because we're just using the definition of what a definite integral is. Okay, Now, it seems like we have two unknowns, and that doesn't necessarily help us, but we actually already have the value of W of 20, which turns our problem into just kind of a basic algebra question. So we know that W of 20 is 71. So instead of that, we're going to write 71. So now I have 2.04315 equals W of 25 minus 71. All that leaves me to do is add 71 to both sides. Again, just a basic algebra question. So I get 73.04315 equals W of 25, which means our temperature of the water at time equals 25 minutes is going to be 73.04315 degrees Fahrenheit.